So I got cut off there looking at the fan pump. So again, it's got the actuator, it's a variable displacement axial piston pump, and it's also got some controls on here. They're a little different than your typical load sensing pressure limiting control. And again, there's some electrical input to it. So that is this pump in here. So tandemly mounted on the back of one of the hydrostatic drive pumps. This is our axial piston pump for the fan. There's the controller that's on it. Looks kind of similar to your controller that's on the main implement and steering pump, but this one is quite different because it is electro-hydraulically controlled. This pump is proportionally, the swash plate is moved proportionally, still load sensing, but the load sense signal is managed now electronically. So the ECM on this machine is commanding a solenoid here. This is a fully proportional solenoid. It can get a small amount of current or a large amount of current directed by the engine ECM or the whole machine ECM. And based on temperatures of various components, whether or not the air conditioning is turned on or off, air-to-air aftercooler temperature, radiator temperature, hydraulic and transmission temperatures, there's a strategy built into the ECM that controls the swash plate in that pump, which controls the variable speed fan. So your fan speed is a result of load sense pressure that's controlled electronically. So we'll cover that system when we start into hydrostatics, but it's there. And kind of opens a can of worms for anybody that thought they might want to specialize in engines. You know, now that we've got load sensing hydraulic systems controlling engine cooling, you know, to troubleshoot an engine overheating problem, you got to have a pretty good wrap on load sensing hydraulics and the electronics now that control it. And the industry's really gone that way with fan control. So again, that pump is here. They don't seem to put a letter on this pump, but it's just there. So again, there's our main pump, quite a large pump. Here's our fan pump, dedicated fan pump. I want to look at some of these components in the tank here. At E, it looks like we have a temperature sender for hydraulic temperature. Again, that would be an input to the ECM. One of the inputs that's going to control fan speed, but it's also going to run the hydraulic temperature gauge in the cab. I gotta go around the. So on the front side of the tank here, behind the cab, this harness is labeled. So this bottom sensor, that's our temperature sensor. Above it, we've got a level sensing switch. It's one of those capacitance type switches measuring the level. So some redundancy again because there is a sight glass in the tank, but they realize some operators aren't going to check that, or certainly aren't going to be checking it while they're operating the machine, driving it down the road. So there is a light on the cab for the level. So there's our temperature sender again. The level switch is at L. So they show it like a physical level switch, but it isn't. It's a wet-dry capacitance type switch that's in the cab. So the oil has to bathe it for it to turn the light off. At K here, we've got a full flow return filter with a bypass check valve and also a differential pressure sending unit that picks up the differential pressure, the pressure drop across the filter, and reports filter restriction on the monitor panel in the cab. So I'm up on top of the toolbox side of the machine here where there's a walkway, and in the top of the tank is where we can see the full flow return filter. So it looks like oil's coming back from a couple different places running into the tank here, and there's a cartridge filter installed in here. There's our pressure differential sender that's reporting pressure drop across the filter from the dirty side to the clean side. So that's our tank. Over there we've got a breather on top of the tank. This is a vented tank, but there is a filter breather to keep the air that's going in and to clean. And again, there's our sight glass. I on the schematic at first glance kind of looks like an oil cooler, but then you realize the energy triangles point inward, and you can see a little AC plug-in sort of scribbled on there. So that is an oil heater. So in the bulkhead here on the front of the cab, you can see what looks sort of like a block heater cord in here. So in there is a tank heater which would be a good option in sort of Arctic conditions. Now that looks like a block heater, but it's much lower wattage. A block heater that goes in the engine cooling system of a machine might be 500 to 1,000 watts of power. It gets quite hot because coolant's good with that, but hydraulic oil can't get as hot as engine coolant can, so that's probably only about a 150, 200 watt heater. If you put an engine block heater in there that got really hot, you'd actually burn the oil onto the element. So it's just a low power heater. It's just going to take the edge off the oil in really cold temperatures, so it has to be plugged in, basically around the clock. You wouldn't put that on a timer. J up here is looking at the oil cooler. That's our radiator type, and it's got a bypass. So that's around this side of the machine, the oil cooler. Connections are there. You don't see a bypass like it was drawn on the schematic right at the cooler. The bypass is actually in this block on the bottom of the tank. So the oil comes to that bypass check valve, then runs to the cooler. But if the oil's too thick and viscous to get through the cooler, it can just open the bypass and go into the tank. And then M is the fan motor, which we looked at in the first introductory video, walk around video. But again, as I mentioned, it's a axial piston motor, much like our piston pumps that we saw for the fan and the implement and steering. But this is a motor now, and it's bidirectional. And it is not variable displacement. Even though we got variable fan speed, all the variation in flow rate is done by the electronically controlled pump over there for the fan. The motor is bidirectional, but it's a fixed displacement piston motor. Because it's a piston type motor, it has to have a case drain off it, so L is the case drain line that's going to run back to the tank. Again, unfiltered. Seems that Volvo's not filtering their case drains. They're running them into the tank. So it's fed off of the fan motor, the fan pump, and that through a fan reversing valve that's on an option, but it's on our machine, that reverses the flow to the fan motor. And you can program a purge cycle from the controller in the cab through the dash. You can set it up to reverse the fan every hour or every 20 minutes or whatever. And if you're working in a dusty environment, you can blow the debris out of the radiators by turning the fan backwards every so often. Or you can do a manual purge. So aside from spending too much time on every single function and looking at exactly what's going on in the 10-bank valve, there's a little more to these DCV spools. As you see, there's small spools next to them, but we'll spend some time looking at that as we get a little further into load sensing hydraulics. But we've covered everything on the schematic. Really, we've been around the whole page here. It starts out looking like a lot of spaghetti, but you realize once you sort of match everything to the component on the machine, it's not that bad. So that is the Volvo G976 implement and steering hydraulic system, with a little bit of a look at the fan as well, and a little bit of a look at hydrostatic drive.